For over 6 decades, crewed spaceflight has operated within a strictly defined safety margin. Astronauts travel predominantly within low Earth orbit, or LEO, an altitude where Earth's magnetosphere still provides a substantial shield against deep space radiation, and the planetary surface is close enough for rapid emergency evacuation. The ARTIS program and the push for commercial spaceflight require a re-evaluation of those survival parameters. Establishing multi-year outposts on the Moon and Mars demands transit and habitation periods of up to 30 months, removing the safety net of proximity and continuous atmospheric shielding. Aerospace medicine categorizes the overarching hazards of these missions using the acronym RIDGE: space radiation, isolation and confinement, distance from Earth, gravity fields, and hostile or closed environments. Historically, research on these stressors has focused entirely on mitigating the physical degradation of fully mature adults. But an extended human presence in space makes human reproduction an operational reality. Every stage of the human reproductive cycle, from the initial division of cells to fetal ontogeny and postnatal brain development, has evolved exclusively under the constant, unidirectional vector of Earth's 1G gravitational field. Extracting the reproductive process from that 1G environment introduces a cascade of biological failures. To sustain a spaceborne population, the medical framework must pivot from treating adult bone loss to navigating the extreme lethality of fetal development in a vacuum. The biological viability of a spaceborne infant is compromised before conception even occurs. Human gametes, specifically ovarian follicles and spermatogenic cells, exhibit extreme sensitivity to galactic cosmic rays, or GCRs, which are high-energy particles originating from outside our solar system. Deep space exposes travelers to high-charge and energy particles, known as HCE. A single direct strike from an HCE particle can shatter the DNA architecture of a reproductive cell. Because cellular repair mechanisms often cannot resolve complex double-strand breaks, any resulting zygote carries a near certainty of severe chromosomal abnormalities. Aerospace agencies currently mandate the categorical disqualification of pregnant crew members. To manage the strict zero-tolerance policy for in-flight conception, astronauts undergo rigorous pre-flight testing and rely on continuous combined hormonal contraceptives or high-dose progestins while in orbit. The cellular environment directly dictates a subject's lifelong health through epigenetic programming. Terrestrial studies on the Dutch famine of 1944 demonstrate how extreme environmental stressors encountered during the earliest stages of programming encode long-term susceptibilities to chronic diseases like diabetes and hypertension. Space introduces stressors magnitudes more severe. Because the maternal host in space is subjected to continuous radiation, altered fluid dynamics, and toxic chemical exposure, the physical environment is hostile to early embryogenesis. The first viable step for extraterrestrial reproduction requires completely removing the conception process from the human body. Organizations like Spaceborne United are actively engineering a bypass to the maternal variable through the ARTIS program, Assisted Reproductive Technology in Space. The system uses miniaturized, automated in vitro fertilization incubators. By simulating partial gravity through a mechanized centrifuge, researchers can begin calibrating the exact physical thresholds required for healthy mammalian cell division, isolating the embryo from the unpredictable physiological shifts of an astronaut host. Yet, an automated incubator only solves the mechanical problem of conception. Once deployed beyond low Earth orbit, the developing embryo faces the relentless bombardment of high linear energy transfer, or LET, radiation generated by solar particle events. Current aerospace medical guidelines strictly limit total fetal radiation exposure to 1 millisievert for the entire duration of a pregnancy. Maintaining that threshold during a multi-year deep space transit is mathematically impossible with current spacecraft shielding capabilities. This chart tracks the risk of radiation-induced teratogenesis against the early phases of fetal development. During decaband stages 2 and 3, the critical window of early organogenesis, the introduction of ionizing radiation correlates with catastrophic cellular fragmentation, resulting in spontaneous abortion or total developmental arrest. If the embryo survives into decaband stage 4, the acute lethal hazard subsides, but the pathology shifts. The radiation exposure drastically increases the probability of profound structural brain abnormalities, severe organ deformities, and permanent intellectual deficits. Surviving the first trimester in deep space requires the deployment of massive, highly advanced radiation shielding. Without it, the foundational architecture of the human body is corrupted before it ever takes shape. The morphological development of a human fetus relies on continuous mechanical resistance. On Earth, amniotic fluid provides buoyancy that effectively mimics microgravity, but only until the 26th week. After that, the fetus grows too massive for the fluid to counteract, and it begins to experience up to 80% of its actual terrestrial weight. This late gestation gravitational loading forces the cardiovascular and musculoskeletal systems to adapt to physical strain. In a continuous microgravity environment, this vital transition to apparent weight never happens. Pacing becomes highly clinical. The cardiovascular system is the first to degrade. Zero gravity causes a cephalad fluid shift, meaning bodily fluids pool toward the head. This triggers the Henry-Gower reflex, a mechanism where the body suppresses vasopressin and excretes centralized fluid. The total circulatory plasma volume drops by up to 15%, leaving the developing left ventricle of the heart severely hypotrophied from a lack of necessary hemodynamic resistance. Concurrently, the absolute absence of mechanical strain downregulates the genes responsible for skeletal muscle differentiation. The fetus experiences profound muscular hypertrophy, severely limiting the development of the slow-twitch muscle fibers required for postural endurance, specifically within the spinal extensors and lower extremities. The skeletal architecture degrades in tandem. Osteoblasts, the cells responsible for de novo bone formation, act as mechanotransducers. Without gravity signaling them to proliferate and mineralize, osteoblastogenesis is directly inhibited. The fetus develops severe hypoplasia and osteopenia. The infant gestated in zero gravity is constructed with fragile, under-mineralized bones and an atrophied muscular system. It is born with a biomechanical framework incapable of supporting its own mass. The nervous system requires Earth's gravity to map its internal networks. During embryonic development, gravitational forces physically assist in the bending and shaping of the neural tube, which differentiates into the brain and spinal cord. Without this cue, the neural tube grows linearly, risking catastrophic central nervous system malformations. The continuous lack of gravity also alters cerebrospinal fluid, or CSF, dynamics. The lack of downward pressure causes the brain to physically shift upward and backward within the skull, expanding perivascular spaces and compressing adjacent neural tissues. This upward shift restricts pristine CSF circulation through the glymphatic system. It mirrors the pathology of spaceflight-associated neuroocular syndrome, or SANS. In a developing infant, restricted fluid outflow prevents the clearance of metabolic waste, allowing toxic byproducts to accumulate and restrict the oxygen necessary for rapid synaptic pruning. The brain's critical period, a narrow developmental window where neuronal circuits require specific environmental stimuli to mature, maps entirely to weightlessness. Without a static gravitational pull, the axons in the vestibular organs remain unbranched or wire themselves chaotically to compensate for the missing sensory input. The infant's perspective motor control calibrates to the physics of zero-G. The neural pathways governing posture, gaze stabilization, and proprioception optimize for a weightless environment, leaving the biological system unable to process gravitational acceleration. Childbirth on Earth relies heavily on gravitational assistance. In a microgravity environment, Newton's third law dictates that the immense physical force required to push the fetus through the birth canal simply propels the mother in the opposite direction. The lack of gravity prevents the fetal head from naturally engaging with the pelvic inlet, increasing the risk of umbilical cord prolapse. The only mathematically viable posture requires the mother to be rigidly tethered to a stationary surface in a squatting position. This aligns the birth canal vertically and circumvents supine hypotension syndrome, a condition where the uterus compresses the inferior vena cava. Delivery introduces an immediate physical hazard. In zero gravity, amniotic fluid, maternal blood, and placental tissues do not drain downward. Dictated by surface tension, they form floating spherical droplets that pose severe asphyxiation risks to the newborn and the medical crew, requiring advanced vacuum containment fields to manage the biohazard. The infant's immune system faces a secondary, invisible threat. The human gut microbiome requires diverse environmental microbes to synthesize vitamins and program the innate immune system. A deep space habitat is a heavily scrubbed, sterile environment, depriving the newborn of the biodiversity required to develop pattern recognition receptors. While the infant develops severe dysbiosis, the opportunistic bacteria that survive inside the spacecraft grow highly aggressive. Pathogens like Escherichia coli grown aboard the ISS exhibit a 13-fold increase in bacterial cell count, thickened cell envelopes, and a pronounced resistance to antibiotics. The active birth in space immediately subjects the neonate to a compounded crisis: mechanical delivery failure, mid-air asphyxiation hazards, and an underdeveloped hyperinflammatory immune system battling antibiotic-resistant pathogens. The aerospace medical community shares a unified consensus. Biological survival and reproduction in space absolutely mandate the implementation of continuous artificial gravity. It is an absolute biological necessity. Because resistive exercise cannot be applied to a fetus in utero, the physical environment of the spacecraft itself must generate the load. This requires massive, continuously rotating space habitats, like the proposed Access Station, engineered to generate centripetal acceleration that accurately mimics Earth's 1G pull. Alternative hypergravity therapies, such as short-arm human centrifugation, or SAHC, apply intermittent bursts of gravitational loading to adult astronauts. But mammalian morphogenesis requires a continuous, uninterrupted vector to correctly wire the neural tube and the vestibular apparatus. Intermittent gravity introduces conflicting sensory paradigms to a developing brain. A healthy spaceborne population cannot rely on pharmacological patches or physical therapy. It requires macro-engineering on a colossal scale to artificially replicate the exact mechanical physics of the terrestrial womb. The culmination of these physical deviations forces a final bioethical question. If a human is successfully gestated and raised in the microgravity of space, could they ever migrate to Earth? This side-by-side model demonstrates normal 1G blood flow compared to a 0G adapted system. The spaceborne cardiovascular system, built with a hypotrophied left ventricle, has no capacity to push blood upward against a 1G gradient. Entering Earth's gravity well results in acute orthostatic intolerance. Blood pools instantly in the lower extremities, causing cerebral ischemia upon any attempt to stand upright. Simultaneously, the skeletal structure buckles. Bones mineralized without mechanical stress mirror profound osteoporosis. The pelvis, femur, and load-bearing spinal column become acutely susceptible to spontaneous stress fractures, simply from the physical weight of the individual's own body. This biological trap is compounded by a legal void. The 1967 Outer Space Treaty dictates a state retains jurisdiction over registered space objects, but the determination of citizenship and human rights for a spaceborne entity remains deeply contested, carrying the risk of rendering the child legally stateless. Adult astronauts accept the severe risks of spaceflight through rigorous, voluntary, informed consent. A spaceborne infant is a non-consenting research subject, gestated by design in an environment known to restrict its morphological and neurological development. Intentionally gestating a human in space permanently tethers their survival to artificial life support systems. It engineers a physical disadvantage that inherently denies them the physical capacity to survive on their ancestral homeworld. Until artificial gravity and absolute radiation shielding are perfected, human reproduction in space remains an insurmountable bioethical dead end.